Hello everybody, thank you for coming for my seminar. My name is Felipe Gabriel, and I will talk about the new kind of transistor that Intel are producing. But to talk about this new transistor, we have to view why the FET transistor have evolved. So, these are schedule, and if you don't do electrical engineering, or you were lost in an island for the last 60 decades, you don't know what is a transistor. So, a transistor is an electronic device that basically works as a switch or as an amplifier. This hydraulic analogy is a good view of how a transistor works. When you put pressure on the piston here, we can let the flow of water or the flow of something go through the big pipe. We have basically two kinds of transistor: the MOSFET, the FET transistor, the field effect gate, field effect transistor, and the bipolar transistors. In semiconductors with a heavy density of transistors, the most used are the MOSFET type. Why they use the MOSFET type? Because you can make MOSFET transistors smaller than bipolar transistors, and they are cheaper to make. Here is an explanation of how a MOSFET transistor works. We basically have ampere type substrate of silicon and the source and the drain with another type of silicon, the N-type. We have here an isolate material, silicon oxide, and we have the gate. When we put a voltage between the gate and the body of the transistor, we allow any channel where we can create a channel here of linking the source with the drain and allow the electrons to flow through it. Okay, this is another view of the transistor. That's showing the regions of this. So, the first improvement in the MOSFET transistor was the CMOS device. A CMOS device is basically two FET transistors in the same space, in the same die. We can control the gate of this transistor I put together, and with one signal we can control the flow of the current in both transistors using just one signal, the signal on the gate. So why this is good for this kind of device? The characteristics of this device are: he have high noise immunity in the static state, a low static power consumption, because we just expend a good amount of current when we switch a MOSFET transistor, when we put it to high or down. When this is in static state, when we put this on the state, this is not consume a lot of current. And this is reflecting a better performance per watt, dissipate less power. So, the lithography process is how the transistors are making. A good exemplification of this is when you go and make a PCB layout and you print it on a toner printer, and then you put in a copper surface and pass the heat, and we put the toner, that's a plastic, in this copper surface. When we put this in with a bottle with acid, we corrose the copper part, and the part with plastic are not corrosive. So we can make this kind of thing. We can make layers. The Moore's law. Who was Moore? Moore was a co-founder of the Intel Corporation that suggests a law that the number of transistors that can be placed inexpensively on an integrated circuit doubles approximately every 2 years. So this is the Moore's law line, and as you can see, this law is being followed through the years. We almost have the number of transistors following this law. To keep following this law, the hindrance have to make transistors smaller, but they found some problems with this. When you try to put smaller transistors in the same die. To try to solve these problems, they changed, for example, the oxide layer in the MOSFET transistor. The silicon, the old type of oxide, the silicon oxide, doesn't work well in a length of 2 nanometers. When you get it too much thin, we have an effect called quantum tunneling in a significant amount. Let me show you what is this. This is quantum tunneling. We have here an isolated material. We have here a package of electrons. And when this shocks this isolated material, this pass through it, this tunneling through it, quantum tunneling through it. And if we get a significant amount of electrons tunneling, we don't have an off stage very well in the MOSFET transistor. We have a leakage flow of current in this. This is not good. We lost power. We have more power dissipation with this. To try to solve this, they changed the type of the oxide layer, the type of the material. They called them as high-K materials. This is a material with high dielectric constant in comparison with the silicon oxide. Then Intel used this material to produce the 45 nanometers transistor that they make. For Intel, it's extremely important to follow the Moore's law, because Moore's is a co-founder of this company, and this is pretty important for them to follow the law. This is for quantum tunneling. Other problem that they face is the short channel effect. When we are getting too small the transistors, if you remember the slide that showed the effect transistor, we put almost together the N parts of the transistor, and these make the short channel effect. Between the N channel, the N type of silicon and the P type of silicon, we have this depletion layer. Okay? And when this is small enough when this is small enough, we can have the flow of electrons through them without having a channel in this, and we have a leakage current again, and a modification of the threshold voltage. The threshold voltage is the minimum voltage to create a channel in the MOSFET type transistor. Here's a picture of it. The P substrate and the N parts of the transistor. When you put it too close, we don't need more this channel here. The electrons pass through them directly, and this does not work as a transistor should work. So to solve the problem of the short circuit, they are making a multi-gate device. So what is a multi-gate device? This is a good view of this. In a single gate device, we have here treat the channel of a transistor as a pipe, a big pipe. And here we have a gate. The gate controls the flow of the current on the transistor. And if we had just one big channel and one big gate, this is more difficult to close this pipe. And what they did, they split these big channels in small channels, and the big gate and small gates, and let in the control of the current flow and the control of the current flow is better in this kind of device. This is another thing we have to talk about is the types of making the transistors. We have the planar types of transistors. We have just one layer. They are in one layer. We don't have a high in them. But when you make a multi-gate device in this kind of transistors, like planar transistors, we have the problem with the size. We have to have the most flow of current that in this big pipe. So the area needs to be the same. And when we split this and put this on a planar layer, we make them too much wide. And this is not good because we need to put more transistors in a die. To solve this, they implement a non-planar transistor for a multi-gate device. We have here the problem of the size solved. We just turn up the multi-gate device, the linear type, like this. But as you can remember, or I hope you can remember, the lithography process is just for one layer. We don't put another layers above of this. So this is a big problem to the hindrance to make this kind of transistor. So how they make this? They basically cut the P substrate like here, and the gate they put in another substrate and just flip and put together. You have two blocks and you put together above the other. Now let's talk about the CMOS 3-gate transistor of the Intel. It's a little dark, but this is a normal transistor with a planar type of transistor. We have the gate here, the gate here, the source and the drain, the current flows through here. And here we have the 3D transistors of Intel. If you can see here, the surface of the source and the drain is higher. We have a third 3 dimension here. And the current can flow not just in the planar surface. We have the current flow here, here, and the other side. The gate control these 3 sides of the current. This is more like this. We have the gate, in here we have the channels. The channels here, and the gate here. The gates here. This is another view. This is a better view of them. So here we have the oxide layer with a high-K material, the substrate, the gate that involves the channel, and this is the 22 nanometers transistors of Intel. This is an evolution timeline of the Intel transistors. In 2003, they were making these transistors, the 90 nanometer transistors, and in 2007, when they get the 45 nanometers transistors, they start to use the high-K materials that I told before. And here in 2011, they are making the 22 nanometers. This is an electronic microscopic view of the transistors, and we have here, this is the gate. Those are the gates. And here we have a source and a drain, a source and a drain. What's the future of the technology of the FET transistors? For 2030, in the Intel schedule, we have the 16 nanometer transistors. In 2015, we have the 11 nanometer transistor. When we get this on the 11 nanometer, we have a big problem, because the lithography process will not work anymore. Using the high-K materials as in the oxide layer will not work, because the quantum tunneling will occur too much that they can make it with high-K materials. So they will have to find another way of making transistors, or another technique to produce them, or to begin a new capítulo in the history of the semiconductors. So that's it. If you have some questions, you can make in Portuguese or in English. No. Não vai aumentar o preço, até porque quando se faz uma mudança dessas, todos os produtos produzidos pela empresa vão ser usados essa mesma tecnologia. E como você pode fazer transistores menores, colocar numa mesma pastilha, você gasta menos silício, então é mais interessante para a empresa, porque fazer o silício 100% puro é extremamente caro, é a parte cara do processo, e se você consegue diminuir o gasto de silício, você acaba aumentando o lucro no final das contas. Mais alguma pergunta? Sim, os processadores da Intel Sandbridge, esqueci o codinome, mas que serão lançados esse ano, já vem com esse tipo de transistor. Já vão vir com esse tipo de transistor. Alguma outra pergunta? O que eu sei é que a frequência do silício é até 5 GHz, alguma coisa assim, porque além disso você começa a ter problemas aqui, ó, começa a esquentar demais, e quando você esquenta demais, você acaba com essa imunidade aqui, essa imunidade a ruídos, porque os elétrons acabam se mexendo com o calor mais do que deveriam. Então 5 GHz é o limite, por isso que eles têm aumentado o número de transistores em vez de aumentar a frequência do processador. Tem colocado vários cores ali para dar conta do recado, tipo, dar separar o trabalho entre mais pessoas ali. Mais alguma? Não? Pessoal, só me desculpem pelo meu inglês macarrônico aqui, foi horrível, mas obrigado pela atenção de todos por terem vindo.